Today we're going to do Chapter 10, Day 9, where we're going to be using parametric equations to help us find and talk about projectile motion. Here are the two general formulas and equations we're going to be using, where x represents the horizontal distance in feet and y is going to be the vertical distance in feet, where both of them are relating to time since the launch in seconds. Okay, so for our first example here, Clint's throwing a ball straight up with an initial velocity of 50 feet per second from a height of 6 feet. So the first thing we want to do is represent the horizontal distance with our equation there. Velocity is 50 feet per second. Cosine of the angle, well, because he's throwing it straight up, that angle is going to be 90 degrees. Then times t. And then when we go ahead and simplify that, in this case we can because cosine of 90 is 0. We know that our horizontal distance equation is just going to be x equals 0. For the vertical distance equation, again, plug in all the parts that you know. We end up with 90 degrees, again, still is our angle because it hasn't changed. Initial height of 6. If we evaluate the parts that we know, we get negative 16t squared plus 50t plus 6. So that's how you find your horizontal and vertical distance equations for your parametric equation. Now it says simulate the motion of the ball by graphing your equations. We're going to go ahead and show you how to do that on the calculator so we can get a visual of what's going on here. So the first thing you want to do here if you're using the Chromebook calculator is make sure every time you open it, after you've closed the app, you have to redo all the modes and all the settings. Otherwise, it's going to restart itself. So first thing we want to do is go to mode. And we've always been dealing in the function mode. This is for our rectangular graphs. Now we got to talk about parametric if we have parametric equations. We're going to be using the rectangular mode quite a bit here still, but because we want to just see a visual of what's going on, you're in the parametric mode. Notice when you hit y equals, we now have x1, y1 with respect to t. So we're going to fill out our equations based on those. And then what we like to do here is go all the way to the left, hit enter. And so that we can see the projectile in motion, change this, go to the right so that it looks kind of like a key, and we'll get a visual on this actual ball in motion. If you have a regular calculator at home, just hit enter on the left side until it keeps blinking and then it comes up with this symbol. So now we're good there. And then the last thing that we're going to kind of do before we get started is we want to change the window so that we can actually get a visual, at least an idea of where we're at. So this ball is being thrown from 6 feet up, meaning that the vertical height is going to be at least starting 6 feet in the air. So let's go with 0 as the ground, and then 6 feet up, we're looking 10 feet high. We can expand this a little bit. Let's go to 20 just to be safe. And then the horizontal distance, because he's throwing it straight up, we don't care about the horizontal distance. So we can either leave it at negative 10 to 10, or I'm going to even zoom in a little bit because there's no reason to have it that wide. So again, we're looking 5 feet left and right from the ground, 0 up to 20 feet high, and we'll kind of try to get a visual of what's going on there. So the last part that's new to you guys here is T-min, T-max. So T-min is we're starting at 0. So we're going to start from the second he throws the ball. And the T-max is how long are we graphing this equation, okay? If I make this 1,000, it's going to graph 1,000 seconds worth of coordinates. We don't want that. It's going to take too long. We won't be able to stop it. So let's go ahead and just say threw the ball up for, 3 seconds, okay? T-step is how many seconds is it taking for them to do each point. So if I say 1, they're only going to graph 3 points. They're going to graph 1 second, 2 seconds, 3 seconds, and it's going to go too quick. We want to see this ball in motion. So let's slow it down a little bit and say 0.01. Again, if you go 0.001, it's going to go really, really, really slow, and it might take a while to finish graphing. So this will just be our starting points, and again, we're going to probably have to adjust them as we go, but this is where we're going to start at based on what we've thought. Let's go ahead and hit graph, and we see the ball started here. It went up. It's off the screen. It's still graphing because that's spinning up there. and it came back down, and you notice it stopped right here. It didn't even finish coming down, which is kind of strange to us because this ball has to finish through and hit the ground, again, because of gravity. So what we're going to do here is we first got to expand our Y max. So let's go to Window. We got to expand our Y max. It might take you a couple tries to get it, but I'm going to go ahead and make it 50. And then we also know that we have to change the time that it graphed because it cut the graph short of hitting the ground. And we got to make sure on part B, how long is the ball in the air? We want to see it come all the way back down to the ground. So we're going to go ahead and make this 5 seconds because it wasn't far off the ground. So let's go ahead and say 5 seconds. The last thing I want to do here that I'm going to point out on this problem in particular, and it's only because he's throwing it straight up, this whole thing's graphed on the y-axis. So those of you that might be at home, if you don't have the colored line on your calculator, you might not have even seen it being graphed. You might have just seen the ball moving. So I'm going to go ahead and go to Format, Second Format, and I'm going to take off the axes so that it doesn't even show it. So now when we hit graph, you see the ball being thrown from 6 feet high. Remember, the bottom of this is 0. That's the ground. It goes up. This is the highest point that it gets. It comes back down, and now we get a chance to actually see it hit the ground. And again, it's still graphing, but we don't need to see anything beyond that. That's why it's still spinning. Okay? So there's your simulation of the motion. Now let's go ahead and start to calculate some other things. So for part B, it says how long is the ball in the air? Well, how long is the ball in the air? That's all depending upon the vertical distance, which is this equation right here. It doesn't really have anything to do with that equation. That's the horizontal distance. So what we want to do is make the y equation equal to 0. So this is where we're going to go ahead and go back to our rectangular mode. So we're going to go back to function, and we need to have it in function mode. And when we go to y equals, we're only going to use this equation, because right now what we want is we want the vertical distance to be 0 as it relates to t, because we said how long. So we need this vertical distance to be 0 and solve for t. So we're going to use that equation right there. Plus 50t plus 6. And now, again, even though it says x, we know that the independent variable is representing time. Okay? So again, if we can go back to, I like to go zoom 6 just to reset. Oh, let's put the axes back on there. So we can actually see this is when it's being thrown. This is when it hits the ground. Okay? Now again, we got to go up so that we can see the top of this. So go to Y max. We know it got to a height of about 50 because we made the Y max 50 and it didn't quite make it there. So we'll make the Y max 50 again. So the ball goes up, ball comes down. And again, it's not traveling anywhere horizontally. We already saw that on the parametric equation. It went straight up and down, but now because the independent axis is our time, we see the vertical height as time is progressing. So this is what we got to find here. The way we do that is hit second, calculate. We want to find a 0. It's a root. Hit enter, and then this is about 2 seconds. So I'll say 2, enter. That's the left side. Now I need to be on the right side, so I'll go to 4 or 5. We'll go 5, hit enter. And then these little bars are saying, is your 0 between these two bars? Yep, hit enter, and it'll give me that intersection. So the ball hits the ground at about 3.24 seconds. So at about 3.24 seconds, the ball is going to hit the ground. The other part for part C that it's asking, when is the ball at its maximum height? And then what is the maximum height? Well, again, it has nothing to do with our horizontal equation because it's just going straight up and down. So we can still use this exact same rectangular equation because it represents the vertical height in terms of time. So now we just got to go second, calculate, find the maximum. So we're going to go again left bound. I'm going to go, I don't know, oh, not 2. Let's go 1. So right here, is this on the left side of our max? Yep. Then pick a value on the right side of our max. Let's go 3. Yep, that's on the right side of the max. So is your maximum between those two lines? Are they pointing to it? Yep. Hit enter. And the maximum says at time 1.56. So at 1.56 seconds, you will have a maximum height of 45.06 feet. So that's how we're using the parametric equations to see the ball in motion as the horizontal distance with the vertical distance. But then we need to determine if we're looking at time, are we talking about the vertical distance with respect to time or the horizontal distance with respect to time? For example number 2, I already kind of filled out the 2 parametric equations for you right there. It says, so find the parametric equation that model the positions of the ball as a function of time. So as we did with the last one, again, our initial velocity is 100 feet per second. The angle is 70 degrees. So our horizontal position is 100 cosine of 70 degrees t. And then the vertical position would then be there. Now, again, for these ones, cosine of 70 and sine of 70, we cannot actually find the exact values. So we'll just leave them as that. When we go to actually graph it, notice that the horizontal position will actually change. So now when we go back to our calculator here, we need to go back into our parametric mode because we're going to simulate the motion of the ball. So we're going to go here, back to parametric mode, go to our y equals. We have 100 cosine of 70. Make sure that now that we're actually using the cosine of 70, make sure that when we close it, t, negative 16 t squared plus 50, actually 100 sine of 70, close it t, and then plus 5. As I was going to say, make sure that now that we're talking about in terms of sine and cosine, make sure that in our mode we are in degrees because, again, as we stated, the calculator on the Chromebook automatically starts in radians mode, so we got to make sure we're in degrees mode. Now, let's think through this. It's got to have an initial height of 5. So again, if we go to our window, we need the y min. Let's go y min 0. Again, that's the ground. Y max, we'll just leave it at 50. It's going to be at 5 and then thrown up, and we'll see how high it goes. If it's up at an angle of 70 degrees, it's probably going to go pretty high at an initial speed of 100 feet per second. So you know what? Let's go ahead and actually make this a little bit bigger because after 1 second, it's not going to be quite 100 feet, but it'll get pretty high up there. So you know what? Let's go up to like, I don't know, 250, and we'll play around with it and see how much we need there. That might even be too much. So now if we look at the x values, we're throwing it from 0, right? So we can even say 0 there, or we can go -3, just give us a little bit of room. And then the x max, if we're throwing it upward at 100 feet per second for a degree of 70 degrees, it's going to go quite a long way. So let's go ahead and put this at 25, and then we'll see where we're at with that. Again, time, no, I accidentally hit trace. We'll see how that goes. Okay, so we see how this ball is going here. Again, our max up here is 250. Our max over here is, what do we say, 25. So that ball was still going up. So we can clearly lower our y value here, but we definitely need to expand our x value. So we'll go back to the window. Let's take our y max, and we'll go to 150. Let's cut out 100 and see where we're at. And then x max, let's go, I mean, that thing was still going up. So let's go 250. We'll flip these. You know what? We'll see how that goes. So there's the ball going up. Oh, we didn't change our steps, so it looks a little goofy, but that ball goes up. Come on. There we go. Coming back down. So that's the trajectory of the ball at 100 feet per second. Remember, our x values are representing the horizontal distance. The y values are the vertical height. Now, again, it stopped here. That doesn't mean the ball just vanished in thin air. It means that our time didn't account for the ball to come actually all the way down. So let's go back to our window. It's kind of bothering me that the x scale is so small. So let's go up by, I don't know, 50 there. We'll expand that. Same thing with the y scale. That was bothering me. Go to the t. We need to go for longer than 5 seconds because it didn't have time to make it down. So let's go 7 seconds. It was on its way down, so hopefully it'll make it down to the ground this time. So there's the ball being launched from 5 feet up, 100 feet per second at 70 degrees. Caps out somewhere up here, and this we said was, what did we say? It was like 200, 250, or 150, I think. So it's going to be pretty close to 150. This was 250. So we can kind of see what's going on there. So that's simulating the motion of the ball. Again, x is the horizontal distance, y is the vertical distance. But now if we want to answer these other questions, how long is the ball in the air? How long is that actually happening? Well, the vertical height is the one that we have to look at here. So now we're going to go back to our calculator. We got to go back to the rectangular mode or the function mode, and we need to plug in this equation. So negative 16t squared plus 100 sine of 70 t plus 5. Hit graph. Ooh. See how it came all the way back in? That's because this is representing time, not necessarily the horizontal distance. So now we need to adjust our window and get way back in there. X max is way too far. How long do we think that ball was in the air? Couldn't have been that long. Let's go 5. Let's see. Went up. Ooh, a little bit short. Let's go 7. Goes up, comes down. Perfect. Okay, how long was this ball in the air? Let's go second trace. We're going 0. And again, let's go 4. And then 6.5. Perfect. Send it in the middle. So the ball was in the air for 5.9 seconds. Taking a look at the horizontal distance. So now, notice for this one, the horizontal distance, how long did it travel? Here is what we're going to be looking at. So how horizontally did it travel? Well, the ball hit the ground 5.9 seconds later. So we want to know on our horizontal graph, at time 5.9, at t is 5.9, what was our x value? So we're going to go with this graph, and we're going to have to plug that one in. So 100 cosine 70 t, graph it, and we want to know at 5.9. So we need our x value to be within that range. We can move the y if we want. Let's go 500. Okay, so then y, second trace, just click value, and when the time was 5.9 on the x for time, what was the horizontal distance on our dependent axis? Oh, sorry. Value 5.9. So when time was 5.9, we were 201.79 feet away. So we have x equals 201.79. And that's how far it was horizontally. Maximum height of the ball when this happens. So again, when we do this, we got to go back to our vertical one, which we said was negative 16 t squared plus 100 sine of 70 t plus 5. Oh, we got to close that. T plus 5. Hit graph. There's the actual arc of the vertical height over time. So second trace, do your maximum. That's good there. 180, I don't know. Oh, that's too far. Second trace, maximum. That's good. We're just going to slide it over. So then our max is 2.9793, 2.94. So at time 2.94, we had our maximum height of 142.97 feet. So that's when the maximum happens, the max height, that's when it happened.